welcome back to a new session. Last time we started the hypothesis testing on chapter 8, which is the last chapter before our final exam. So, which we have seen that, the full process, which was the last question, we have seen that the p-value way was in the z-score. Right? So two things that about the claim about the mu, right, the population mean. If sigma is given, then we use the z-score, right, z-test. The test statistic will be z-test. Then we use the p-value. The p-value method, right? If p is less than the significant level alpha, then we reject the null hypothesis, right? Reject HO. And also in the case that when sigma is unknown, we use the t distribution and the t statistic, and we're following the traditional method, which we didn't see yet, but we will see that later today. Find the traditional method. Both of them, we need to draw a simple conclusion to see what we can conclude about the mu, right, about the population mean. So basically, the null and alternative hypotheses are the claim, right, are the statement of the population parameter. We're here focusing on the population mean, and it was discussed before that it could be a population parameter, it could be a population variance or population standard deviation. Right? All of them could be able, even like for different populations, we could compare if they are from the same population or they are from different population by comparing their difference of the population mean also. Even though maybe population mean are same, they could be from different population. That also happens. Right? So a lot of things it can do, not only here, but this population mean is just the introduction to get a brief idea what's the test statistic, what is the p-value, and what is the traditional method, what they can help us to make decision about it, right, about the population parameter. So also last time what we had seen was the first example about the body temperature stuff, and given the population parameter, population standard deviation. Well, let's see some more example about them. Also, we have a simple random sample from a certain population had a mean age of 27. Right, the age of this population is normally distributed of 4.5. Right, to be less confused, we put two columns here. That's the simple random sample of 10 people, which those are selected from a certain population, has a mean age of 27. That means those 10 people has mean age of 27. The middle is just provided extra information that is from a certain population, right? And what is given is the age of this population is normally distributed with a standard deviation of 4.5. It follows the idea of central limit theorem, right? That the sample mean is following normal distribution if the original is normally distributed, right? And given the standard deviation of the population is 4.5. Also, a couple information I will give it. Then this third sentence here is, well, from the sample have a mean of 27, right? Researchers suggest that the mean age of this given population is below 30, which the 30 years old was the data, the old data shown, right? The old data suggested. Magnificent. I try to test his claim under 5% significance level. Right. So what we give? We're given that a simple random sample of 10 people. The mean age of this sample is 27, as we show. The population is normally distributed, therefore we don't need large sample if it's normally distributed, with a standard deviation of 4.5. So the condition of normal satisfies, the condition of central limit theorem basically satisfies. Based on this sample, research suggests that the mean age of this population is below 30, which the old data show the population mean of the age is 30. I test his claim on the 5% significance level. That's all the information we know. Then let's try to follow the steps. The first step is to be clear what are the null and alternative hypotheses. The null is the assumption that the mean age was 30 as shown below, and how likely we can get the sample, right? And the alternative hypothesis is saying, well, from this sample of 10 people that it may be below. So the alternative is a doubt. that from what we see, well, we maybe see the mean age of this group maybe is below 30, since we get a group of 27 as the mean age. And what we get is sample mean is 27. Given the population standard deviation is 4.5. A group of 10 people with alpha to be 5%. Right, and that's all the information we know, right? We get from the question. Then which this one shows it is the left tail test. Right, because it's below. So when we draw the density curve, we draw the left tail test. We draw the shaded area to the left. And then we give it all that. Then the denominator part we are able to calculate out before we go to the formula to find out the z-test, z-score, right? The z-test score. Statistics, in other words, right? The test statistics. And the standard deviation is 4.5. Sample size is 10. When we divide it, we keep as many as decimal places we want to. It could be 1.42302. We could keep as much as decimal places, as many decimal places, but the more the better, of course. Right? So keep more. Then go to the test statistics. The z star x minus the mean over sigma over radical n, which is the looks more or less like the central limit theorem formula. Right, the mean is the population mean, actually is the mean of the sample mean. This standard deviation over radical n actually is the standard deviation of the sample mean. Right, what we get, 27 minus 30 divided by 1.42302. We get subtraction, get negative 3 divided by 1.42302, we get negative 2.11. Right, since it's left tail test, we get negative 2.11. That is the density curve. So we get p-value is, well, we just go to the table, right, of negative 2.11. That is 0.0222. Our alpha is 0.05, so it's less than alpha. So our conclusion say, well, our decision is to reject the null hypotheses, accept HA, the mean is less than 30. Right, so for the conclusion, we do not have to write the long sentence. Right? If you want to, you could say, well, you could state the reason. Right? If the mean age of this population is 30, the probability we get a group of 10 people with mean age of 27 or below is only 0.02 to 2, which is very small. So therefore, since it's very unlikely to get that group of sample and that extreme, we can say we have strong evidence that the true mean of this population is below 30 Pearson. Right, because the p-value is less than alpha, then we make decision is reject the null and accept the alternative. Right, the set population mean, therefore is lower than 30. Such conclusion we can say, well, we have a strong evidence that the true mean of this population is below 30. Right, strong enough is because, well, it is a little far away from 5%. It's only 2% to get that type of sample mean age of 27 for the 10 people and the lower, right? And 27 or lower for the 10 people. Right, so for this claim here, it said below 30, then that is the left tail test. After we find the z-score, whatever it is, we cut it to the left, then to find the p-value. Well, we just go to the z-table for the negative 2.11, and we'll go to table. Negative 2.11. Let's see. Well, when I go to the z-table, I have find something was not right. 0174. I find the little things issue or error on my notes, which I had done before, that I look into the table with a wrong row. Right, the actual p-value is even smaller of 0.0174. It's only 1.7%. Right, it's even lower, but still the result will be saying reject the null hypothesis. Right, it is the negative z-score of negative 2.11 in this case. Right, so that is how we do this question, and I'll go to the next one. Let's see the next question. A simple random sample of 16 male has a mean height of 69.7 inches, right, from a certain population, of course, which the height Well, also the height given that population is normally distributed with a standard deviation of 2.9. Right, so the third sentence says, well, 3 years ago, the population mean height of the man was measured to be 69.1 inches. So from there we can see, well, someone can have a claim that the mean height now may be bigger than the population mean we know before. Right, so actually a researcher find that or think that the mean height of the man from this population is greater or higher than 69.1 inches now. Right, it was 69.1 inches 3 years ago for the true population mean, but we don't know now, right? Test to the claim and the 5% significance level. So what we get? Simple random sample of 16 people, 16 male, has a mean height of 69.7 inches. The height itself is normally distributed with a standard deviation of 2.9. The first one tells us the group of 16 men has a mean height of 69.7 inches. Right, the second sentence tells us the height from this population is normally distributed with a standard deviation of 2.9. It was measured, the mean was 69.1 inches 3 years ago. That was the population mean before. And based on the sample, researchers find that or think about it could be higher than 69.1 inches, which was the mean as we know, as given. And the significance level was 5%. Right, so let's see it. Right, the null hypothesis was the assumption that the man's mean height was still 69.1 inches. And the alternative hypothesis say, well, it could be higher than what we had known before. And what we given was the sample mean with 69.7 inches, the standard deviation, which is a population standard deviation, right? That's asks the whole sentence is saying the population is normal with a standard deviation of 2.9. The sample size we given was 16 and the significance level alpha is 5%. The alternative hypothesis of greater than 69.1 of the mean shows it is a right tail test. Right, then over all these information, we are doing the z-test. Right, so the sigma over radical n is what we find before everything. (2.9) divided by square root of 16, that is 0.725. Right, therefore, our z-score, the test, x bar, the formula, minus mean over sigma over radical n. 69.7 was our was the mean from the sample. The population mean was the assumption, and the denominator was the standard deviation of the sample mean, is 0.725. Now we'll get the subtraction is 0.6 divided by 0.725, that's 0.83. We got the right tail test. For the z-score to be 0.83. Now we get the p-value, which is from the table of positive side, that's 0.83. We use 1 minus the table value. 79767. Which we get the p-value is 0.2 something. Right, when we convert to percentage, that is somehow 20.33%. It's way larger than our alpha. Now, alpha is only 0.05, this one is 0.2033. So we are saying, well, the decision made is fail to reject HO. The mean height is still 69.1 inches. Which means, well, if the assumption holds, then the likelihood to get a group of 16 to have 69.7 inches of the mean height or greater has a probability of 20%. So it's pretty large probability, right, compared to the type 1 error of alpha here, or significant level in other words, of the alpha. That means this event is very likely to happen. Or at least it's not unlikely to happen. You do 5 times, maybe one time you get a 69.7 inches of the mean height or larger. So we don't have evidence. we don't have evidence to support this claim. Well, we don't have evidence to support the claim that the mean height of man is higher than 69.1 inches for this population. Right, therefore, the mean height was tested 3 years ago to be 69.1 inches of the man. It still holds 3 years later, which is now. Right? It still holds. So that is the example here. Still this question given the standard deviation of the population. When we're going through the word standard deviation, we should be super careful, right, of what is it asking or what is it provided. Is it a population standard deviation, or maybe it could be a simple standard deviation? Right, let's see some example which wording a little differently. Let's see. Alright, the question is saying, well, the first sentence, 40 people used the Weight Watchers diet for 1 year. Their mean weight loss was 3.0 pounds. And the standard deviation of their weight loss was 4.9 pounds. Right, so the sentence is kind of throwing to you all the way from the mean to the standard deviation, which the mean was the mean of the weight loss of this sample, and standard deviation was the standard deviation of the weight loss from this 40 people as a sample also. Right, so which means the standard deviation is actually a sample standard deviation. Right, so that is the question provided. Right, it's wording more specifically focusing on this sample instead of the question we see before. Before we see was a little more general, right, from the distribution with the standard deviation of what. Here is a whole sentence about the sample. Right, so read more carefully that we can get the standard deviation here is the standard deviation from the sample, which is the S here. Well, what we're trying to do is use 1% significance level to test the claim that the mean weight loss is greater than 0 pounds. Alright, so that was the question. Right, let's see. Or they say, well, a group of 40 people, weight to lose for 1 year, whatever. The mean of weight to lose was 3 pounds, and the standard deviation 4.9 pounds. And the significance level is 1% to test the claim that the weight loss is greater than 0 of average. Right, so maybe someone is losing weight, someone is gaining weight, but the average is 3.0 pound of losing. Right, so to test if it's greater than 0 pounds. Even though it shows to be greater than 0 pounds, but still doesn't mean this one is very effective, right? It just means it's useful. Let's see. Right, that's all the information.